Hi everyone, welcome to 1.2, Solving Quadratic Equations in the Complex Number System. Recall back in intermediate algebra that you learned you could solve a quadratic equation algebraically using various factoring techniques, completing the square, or through the use of the quadratic formula. You can also solve a quadratic equation graphically by using a graphing calculator to find the x-intercepts, or roots. Let's refresh these findings regarding quadratic equations and then look a little bit deeper. Starting with solving quadratic equations by graphing, see example 1. It says find the solutions to this quadratic y equals x squared plus 4x minus 14. So if I was to solve this by graphing, the first thing I would do is take out my graphing calculator. I would go to y equals, and then I would type in the equation, x squared plus 4x minus 14. And then I would hit graph, and you should see that a graph appears similar to the one that I have displayed on our sheet. To find the actual solutions to this graph, what you're going to have to do is you're going to have to hit the second button, then trace. So let me write this down. So it's going to be second, then the trace button. And then you're going to select number 2, which says 0, which are going to be your x-intercepts or your zeros because they take place with a y value of 0. And then once I do that, at this point, this is where you will do the left bound, which means take your cursor and move it to the left of the x-intercept. Then you'll do right bound, in which you'll take your cursor and move it to the right of the x-intercept, and then you'll select guess. And once I do that, I should get my two answers, which end up being x equals negative 6.243 and x equals 2.243. Moving on to example 2, it says find the solutions to this new quadratic equation, y equals x squared plus 4x plus 5. For this one, I wanted to demonstrate to you how to solve this both graphically as well as algebraically. Let's first look at it graphically. Using the same steps as we did in example 1, I typed my equation in my calculator and I hit graph. But this time you notice that the parabola, the graph of this quadratic, does not hit the x-axis. You'll notice here, no values of my graph hit this x-axis. What that means is that there's no real solutions to this graph. The graph tells us that the roots of the equation are indeed complex numbers, and they will appear in this form a plus or minus bi, which we discussed before. Now let's look at that same equation, but let's solve it algebraically. My preferred choice for solving this quadratic equation algebraically would be to try and factor. In order to factor, I would have to come up with two numbers that multiply to 5 and add to 4. Well, we know that to multiply to 5, positive 5, I would need 5 and 1 or negative 5 and negative 1, since a negative times a negative still is a positive. However, neither of these two options will add up to 4. So since this does not multiply to 5 and add to 4, I cannot factor it. So I wrote here, this quadratic equation is not factorable. So as a rule of thumb, if you can't factor, remember the quadratic formula will solve any quadratic equation. So let's recap what the quadratic formula looks like. To do the quadratic formula, it's x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. So in this problem, I have to identify a, b, and c. A is 1. B is 4, and C is 5. So I'm going to substitute those three values in for A, B, and C. So I get opposite of B, so the opposite of 4 is negative 4, plus or minus the square root of 4 squared minus 4 times A times C, all over 2A, or 2 times 1 in this case. Negative 4 plus or minus, let's clean this up. 2 times 1 on bottom is 2. I have 16 minus 20, which is negative 4. And right off the bat, you should be able to recognize this is why it wasn't factorable. This is an imaginary number, the square root of a negative. We can't do it. No number times itself will ever be a negative. So to simplify this, we got negative 4 plus or minus 2y over 2. And then I can reduce each of these terms by 2. And I get negative 2 plus or minus I. And those would be my complex solutions to this quadratic equation. Notice there's two answers here. Negative 2 plus I and negative 2 minus I. So continuing on, the complex roots from this last example, example 2, we found the answers were x equals negative 2 plus I and x equals negative 2 minus I. These roots are identical except for the sign separating the two terms. One root is negative 2 plus I, and the other root is negative 2 minus I. Roots that possess this pattern are called complex conjugates, or conjugate pairs. This pattern of complex conjugates will occur in every set of complex roots that you'll encounter when solving a quadratic equation. So it's important to note, if the roots of a quadratic equation are imaginary, they're always going to occur in conjugate pairs. Now, as I mentioned before, if we're solving a quadratic and it's got two complex or imaginary solutions, we will not be able to factor it as of now. So I wrote here, factoring as we know it will not give us solutions in the complex number system. We'll extend our knowledge of factoring later. For now, let's focus today on two methods to solve these quadratics, using completing the square and the quadratic formula. I'm going to walk you through two examples that cover each of these. Starting with example 3, solving the quadratic equation using completing the square. I have 2x squared plus 12x plus 20 equals negative 6. In order to solve this by completing the square, step 1 is going to be to subtract the constant from both sides. So I'm going to subtract 20 from both sides. When I do that, I get 2x squared plus 12x equals negative 26. My next step is to divide both sides by the a value in this problem. So in this case, a is 2. So I'm going to divide both sides by 2. And I get x squared plus 6x equals negative 13. Now, step 3 is to complete the square. And in order to complete the square, you're going to use this formula. You take half of b, and then you square it. So my b term is 6, so I'm going to do half of 6. Half of 6 is 3, and then square it is 9. So when I go to write this, I'm going to write x squared plus 6x. I'm going to add in this new c value to both sides. And the reason why I got to add it to both sides is I can't change the equation. I can't change this problem. By adding 9 to the left side of the equal sign and adding 9 to the right side of the equal sign, we're keeping this equation balanced. Nothing really has changed. At this point now, I can go ahead and factor the left side. What multiplies to 9 and adds to 6 is x plus 3 times x plus 3. And on the right side, if I simplify negative 13 plus 9, I get negative 4. Now, x plus 3 times x plus 3, I'm going to rewrite this as a perfect square. X plus 3 squared equals negative 4. And to solve this quadratic, I can go ahead and get rid of this square by square rooting both sides. And the square root of negative 4 is going to be imaginary. So I pull the I out, and the square root of 4 is 2. Now, something you have to remember, whenever you take the square root of both sides in a solving equation, you always need to remember this plus or minus sign. That's going to give us our two distinct solutions or two distinct roots. Now, to finish this problem off, I need to solve for x, so I'm going to subtract 3. And I get x equals negative 3 plus or minus 2i. Remember, we write the real part first, the imaginary part second. So there's two answers to this problem. Both are complex roots, -3 plus 2i, as well as -3 minus 2i. And that's how you complete the square. Moving on to example 4, now we're going to talk about how to solve this one using the quadratic formula. So it's the same exact problem. I'm just going to show you another method to solve it. In class, there might be on assessments where I might tell you which method to use. I might ask specifically for you to use completing the square. Other times I might ask you to use the quadratic formula. And there might be some times where I let you choose whatever method you prefer. So I still want you to be able to do these both ways moving forward. But like I said, there will be some flexibility here and there where I'll give you the option to pick. So let's recap again what the quadratic formula is. X equals opposite of b plus or minus the square root, b squared minus 4ac all over 2a. Let's identify a, b, and c. Now, in order to identify a, b, and c, I'm going to take this equation and I'm going to first bring my constant over to the other side. So I'm going to have 2x squared plus 12x plus 26 equals 0. So whenever we solve using the quadratic formula, we always need our equation to equal 0. So in this case, a is 2, b is 12, c, my constant, is 26. And we can go ahead and plug in 2, 12, and 26 into their respective values for a, b, and c. So we have x equals the opposite of b, so the opposite of 12 is -12, plus or minus, square root of b squared, so 12 squared minus 4ac, all over 2 times a. I'll clean this up. 2 times 2 is 4 on bottom. Inside my calculator, I can go ahead and type this in. 12 squared is 144. And then I have -4 times 2, which is -8. Times that by 26 is -208. So underneath my radical, I need to do 144 minus 208. And I get -12 plus or minus the square root of -64 over 4. And again, this is telling us that this is an imaginary answer, so I got to take the I out. And the square root of 64 is 8. Again, all 3 terms are divisible by 4 in this case. So I have -3 plus or minus 2i as my final answer, which again matches up with the answers that we got in example 3. So again, you can use both methods to solve this. So the last thing I want to talk about today in our notes is how can you tell if you're going to get complex solutions? Just based off the couple of problems that we did today in our notes, you should have a pretty good understanding just by looking at the start of a problem, whether or not you're going to have any complex solutions or not. And it all comes down to what number you get inside the radical, as I noted here. Imaginary or complex roots will occur when the value under this radical portion of the quadratic formula is negative. Notice that the value under the radical portion is represented by b squared minus 4ac. So anytime when you plug in a, b, and c into b squared minus 4ac and you get a negative value, well, that's our indicator that the quadratic equation is going to have 2 complex conjugate roots. So b squared minus 4ac has a name. It's called the discriminant. And the discriminant tells us the nature of the roots of the quadratic equation just by plugging in a, b, and c into that formula, b squared minus 4ac. So when I plug a, b, and c into that formula, if I get a number that is positive or greater than 0, I'm going to have 2 real solutions because the square root of a positive number is a real number. So I would have 2 of those when I take into account this plus or minus sign. If I plug in a, b, and c into the discriminant and I get an answer of 0, well, the square root of 0 is 0. And when I add it to, or subtract it to another number, it's only going to give me 1 solution. And that will be a real solution. And then finally, as we saw in the last example, when I plug a, b, and c in for the discriminant and I get a negative number, well, we know the square root of a negative is imaginary. Therefore, we're going to have 2 complex conjugate roots. If you are trying to determine the type of roots of a quadratic equation, not the actual solutions or roots themselves, you don't have to do this entire quadratic formula. Simply just look at the discriminant. Again, if I'm just asking you for the nature of the roots, whether they're going to be two real, one real, or two imaginary or two complex roots, you can just use the discriminant to find that. But if I ask you to find the actual solutions or roots to the equation, you're going to have to go ahead and solve that using the quadratic formula or completing the square. Good luck with today's homework.